Hello, everyone. Thanks for joining us today for another exciting podcast. Today, we're discussing how 5G is driving the need for a hyper-converged infrastructure at the edge. Today, I'm excited to have with me Joe Speed, who's the head of Edge at Ampere Computing. Those of you who are not familiar with Ampere Computing, it's an American fabless semiconductor company based in Santa Clara. They develop cloud-native server microprocessors. They have an amazing processor called the Ampere Ultra Max. It's a 128-core cloud-native processor that has the lowest power consumption and gives you the greatest performance. It's being used in 5G transportation and other 5G edge segments. Hi, Joe. How are you?
I'm great. Always a pleasure to talk to you, Mondo.
Thanks a lot for joining us today. There's a really exciting topic here. We're relating 5G and how that relates to hyper-converged infrastructure. So you can't go many places today without hearing about 5G. It's revolutionizing the world. Most people are familiar with 5G because of their cell phones or mobile broadbands. But I think people are less familiar with 5G and how it's revolutionizing Industry 4.0 and also the Internet of Things, the small devices that produce data that can travel long distances. So how is 5G enabling new service offerings?
Yeah, so there's a few things going on there. If you look at some of the alphabet soup, the acronyms around this, the enhanced mobile broadband, the EMBB, ultra reliable low latency communications, URL, LLC, massive machine type connectivity. If you kind of dissect what this really means for the kinds of applications you can do, you get more bandwidth, you're able to have lower latency, and you're able to have more things connected. And what that does is it actually opens up the opportunity for new kinds of applications, a whole new class of applications, and applications that frankly were really not possible prior to 5G. And it's these new kinds of applications and all the things that brings that's rather exciting to me.
Interesting. Yeah, I briefly mentioned IoT earlier, the Internet of Things. We all have devices now, such as our Amazon Alexa, even our treadmills, our exercise equipment, little personal devices which transmit data. It's said by 2025, there's going to be 30 billion IoT devices worldwide generating unbelievable amounts of data. Can you explain to us what IoT is, the concept of it, and what can be learned from the data these devices will produce?
Yeah, so IoT, Internet of Things, is a term that got foisted on us in the community by Gartner and the press, the media. It's more properly known as machine to machine. And think of it as the ability for devices to be able to discover one another and interact with one another. And IoT, I think a lot of people are kind of thinking of IoT these days as, because of the nomenclature, as, oh, it's on-ramp to the cloud. But there's actually a lot of value in just within the local, like proximal IoT, of things discovering and working with one another, working with things that are in the same physical proximity.
That's interesting. I went to a demonstration a short while ago where we saw these robot swarms on a factory floor, and they're all communicating with each other at the same time. They're giving each other different tasks to do things in the factory, whether it's getting some tools, whether it's getting information from some office to another. It was fascinating how the coordination from these devices was happening so seamlessly. I've never seen anything like that before. So now to our topic of hyperconvergence. In layman's terms, can you help us understand what that is?
So, Wikipedia's got a nice little blurb on that, but I'll kind of pick it apart for you. So they talk about hyper-converged infrastructure is a software-defined IT infrastructure that virtualizes all of the elements of conventional hardware-defined systems. Hyper-converged infrastructure includes, at a minimum, virtualized computing, software-defined storage, virtualized networking, and typically runs on off-the-shelf servers. So there's a few key things there. One is software defined. Okay, that's really the underpinnings of this is, and there's an analogy in automotive. So in automotive, every discrete function in the vehicle was a dedicated piece of hardware. Okay, so a dedicated microcontroller, MCU, or microprocessor, ECU. And what's happening is all of these functions are becoming written in software and then collapsing into a few larger, more powerful computers. And we see that's what's happening in so many spaces. It's happening in robotics, it's happening in infrastructure, smart city manufacturing, and within the 5G network. And so if you look at the network and what's going on there, you've got the software-defined radio, the ORAN with the software-defined networking, all of these kinds of things, and being able to collapse all of these discrete functions into a piece of hardware or a stack of hardware, and being able to add new capabilities over time. It's really interesting, the kind of flexibility that brings.
That's interesting. I guess that really highlights what you do at Ampere Computing, your company, with the number of cores you have that really facilitates the high degree of virtualization, the containerization, and the open compute. And is that what's really driving hyperconvergence, these advances in processor technology on a single die that you can do so much on and incorporate these different parts of networking and storage?
So that's certainly part of it is, so for us, we're birthed in the cloud native processor. It's all about how do you provide very dense, efficient compute? And, the company, we set out to tackle a set of problems, and one of which is just sustainability, right? Like, if the processors are not dense, if they're too power hungry, you need too many racks, too many data centers. It's bad for the environment, for sustainability, for carbon footprint, all of these kinds of things. Okay. And so we really focus on developing these processors where you can pack a lot of compute per socket and a lot of sockets per rack, and have all of that be even less than the current kind of energy envelope for these racks. And, in the cloud game, you look at some of our customers, Google, Microsoft, Oracle, Hetzner, Equinix, some of these folks on the cloud side, they sell compute, right? So it's like, you take a processor and you imagine you're taking each of these cores and selling them to different customers. And so how do you virtualize that? How do you secure it? Okay. All of these kinds of things. So these are things we were very focused on. Well, it turns out the work we've done there actually lends itself to these things at the edge and, core network, 5G infrastructure, all these other things, because what you're able to do is pack a lot of different functions together, but isolate them in VMs, deploy them using containers, and have this freedom of interference so that, one network function, the demands of it are not interfering with the performance of other network functions.
That's really amazing. Now, you brought up the network edge. It's a perfect segue into the next question. With so much data being produced, an enormous amount of data from robotics, machine to machine, Internet of Things, all this data, you need to move your infrastructure much closer to where the data is being generated to avoid any latencies, to avoid any throughput issues. So how can hyperconverged infrastructure, what's the mechanism to deploy it at the edge and use it at the multi-access edge computing?
Yeah, so, you touch on something really interesting there, which is the edge. The reason the edge has always fascinated me is, it exists out there in the real world, right? Like it's where the people are, it's where the things are, it's where things happen, okay? So that's where data gets created. It's where events happen, it's where data gets created. And ADLINK, like the formation of ADLINK is, A to D, analog to digital. Like it was really all about ADLINK had developed these analog to digital models, data acquisition modules, and realized like, oh, we need the compute right there to process it as the data is being generated. And with the hyperconverged, you have this same kind of thing where like with 5G, a lot of people think of 5G as, oh, I just have a faster on-ramp to the cloud. And that's true. I mean, that 5G will definitely drive a lot of workload to the cloud. But what it also does is because of the bandwidth and because of the low latency, it is creating demand for compute that's physically closer to these devices to where the events are occurring. And whether you're talking about, with the mobile operator or private 5G on-prem or any of these kinds of things, some of the dynamics are the same. And so with the hyper-converged infrastructure, the fact that I can have my software-defined radio, software-defined networking, storage, all these other functions. Well, I can also have compute, and can have compute that's for my dedicated applications. I can have compute that I can sell. I can rent it out. So you can start to do things like, Pokemon Go, right? Like it's an older example, but actually like how do I move the compute, like the game mechanics closer to, if there's 20 people in a park, how do I move the compute closer to where they are so they get this better experience?
That's really interesting. How do you're saying as a service, so I'm envisioning this infrastructure at the edge being close to where that data is being generated. How then does the compute, or what orchestrates these services? Let's say someone suddenly is demanding a tremendous amount more bandwidth. How is that getting orchestrated, those services being delivered on the fly, if you will, or at real time to meet the compute, storage, and networking demands of those devices that come on and off the network edge and demand the scalability?
Yeah, so for this, there's some people that really specialize in it. I dare say it's above my pay grade. There's some people who live and breathe these things. But when you have it virtualized, I think the combination of, VMs, containers, orchestration, right? Kubernetes, OpenShift, these things, and having very dense, energy efficient compute, it allows you to pack more compute into a physically small space, right? Like how much compute can I fit into a shoebox? How much compute can I fit in something the size of a dorm fridge? And then the power efficiency, right? And that's also, it goes hand in hand. Like I can have more dense compute, not just because I have more cores, but because they're efficient. And if it's efficient, I generate less heat. And if I generate less heat, I can pack more of them together into a physically small space. And, and that's how you see things like ADLINK makes this clever little thing that's the size of an iPad mini, and it's 128 cores and up to 768 gig of RAM, and you hold it in your hand, right? So, so that's definitely, some of the building blocks that enable this is taking all this work that was done around how do you pack more compute per rack in the data center, and then figuring out, okay, how do I use that to then put more compute in the mech, hanging off a tower, in a facility, on the factory floor, all of these things.
Right. It sounds like a winning scenario. You can reduce the carbon footprint, you can reduce the energy required to cooling it, and get the services and the scalability you're looking for. Can you tell us about some interesting use cases?
Yeah, I love cars. Cars to me are a lot of fun, and so I've spent a lot of time building various concept, autonomous, whatever, and so like one of the ones I was helping this company, Halo Car. They do uh, it's think it's like rental car, but with like Uber Lyft convenience. So you step off the plane at McLaren Airport in Las Vegas, you pull out the app, and a car rolls up to the curb, and it's driverless. There's nobody in it, and you hop in the car, and then you drive it away, right? And that's all enabled by 5G. And so we took the Halo car out to the Las Vegas Motor Speedway, and it's outfitted with ADLINK computers, and had it be the pace car for the ADLINK computer powered Indy Autonomous Challenge race cars. This was at CES last year, and we had this thing getting up to, I think, 90, 95 miles an hour doing laps of the Las Vegas Motor Speedway. And it's this little, Hyundai EV SUV with no human in the car. There is a human, he's not in the car. The human is in a driving simulator. So think something you'd use for like your F1 racing game. And he's there in the building, trackside, and all of this is over the 5G. So you've got 6 cameras in the vehicle. All those video streams are getting encoded and coming over the 5G. And then displayed in this wraparound simulator, and then he is driving and all of that. So, hand on the wheel, foot on the pedal, and all of that is getting transmitted back to the vehicle, to the drive-by-wire system. And, so it's not AI, it's not autonomous driving. There is a human, but it's this low latency, reliable teleoperation. And that's something you really could not do without the bandwidth and the reliability and the low latency of 5G. So that's one. Another one that's fun, and it didn't use 5G, but it's analogous, is at Narita Airport, our friends at Will, Panasonic Automotive, doing something interesting around autonomous wheelchairs. And in that case, what you have is all of the sensors are in the ceiling, the compute is in a wiring closet, and the wheelchair is being teleoperated, remotely driven through the facility. And, I love these tech for good, right? Things that help people. And that's one that really impressed me.
That is really cool. I mean, I can see how 5G, the advent of 5G really does facilitate those, because previous iterations, I guess, didn't have the bandwidth or the low latency that made those things possible. Thank you for those examples. That was very interesting. Speaking of 5G and HCI, when can we expect these rollouts to occur? Are they already occurring? Is there a timeline for these?
It's already occurring. I too often quote him, but William Gibson, to paraphrase, said the future is already here. It's just not evenly distributed. And that's really a general thing. Like anything we talk about, for the most part, these things already exist and are used and are in production somewhere, just not everywhere. So the hyper-converged infrastructure, you see that in some of the private 5G. So things like mining facilities and other kinds of campus applications where they have dedicated. It's happening with the mobile operators and getting rolled out. And it's really the basis of much of what you'll see at Mobile World Congress here later on this month in Barcelona.
All right. Wow. That's fantastic. This was an absolutely fabulous discussion. It's really nice to understand how the innovations being done at Ampere Computing, the amount of core density you have on those processors, is really helping drive this hyper-converged infrastructure. Amazing technology. Well, thank you very much, Joe. We hope you enjoyed this podcast today on 5G and hyper-converged infrastructure. We welcome your comments, and I want to thank my special guest, Joe Speed. Joe, I hope we get another chance to do something like this again.
Always a pleasure. Anytime.
All right. That ends our podcast for today, and thank you.